Snowball Earth. Let's go. And my microphone is a blue snowball. Ooh, yeah, topical. All right, let's try this. So, as shown in the illustrative photo above, yeah, there was a time when the Earth froze over. Now, the continents weren't arranged like this at all. That is a modern interpretation, but why not? So this is actually Precambrian. There's a period called the Cryogenian, which is right between the Tonian, which is where we get sponges appearing, and the Ediacaran, which is where we get a bunch of stuff appearing, like diversification of animals. And this is in the middle. And we think that the globe, basically, at least the surface, would have frozen solid or very close to frozen solid for 4 separate times. And it may have stayed frozen for thousands to millions of years. Yeah, isn't that something? It is tough to tell very precise geological time. There are very few formations that have rocks of this age, but they're spread out around the world, and they would have been at the time with current tectonic models, and they all tend to show the same things. So what you have during this time are global freezing. The entire globe gets so cold that you basically get solidification of water everywhere. On the surface, there will be liquid water underneath that, like on Europa. Yeah, which is one of the moons of one of the big gas planets. And let's see, whenever it would thaw, it thawed with a vengeance. We had a temperature spike. And this massive increase in temperature corresponded with, we think, gigantic waves and just really destructive conditions. And so that's it. That's your rock and your hard place. Either you're frozen solid or you're being bashed around by the extremely violent oceans, all of which would make it very difficult to live, particularly near the shore, which is going to be the first thing to freeze and the thing that is going to be most disturbed by large waves. Because over the deep ocean, you can't really tell if there's waves up there. It'd probably be hard to tell if there's ice covering up there. You're just too far down. Yeah. So, what we find are glacial deposits that are succeeded by thick deposits of carbonates, which are made underwater, and where they are absorbing a lot of CO2. So you go from ice ball to CO2 greenhouse to ice ball to greenhouse to ice ball to yeah, all of which we think may be instrumental in the way that life developed. Not that life necessarily needed to be pushed to the edge in order to develop, but life probably wouldn't develop in this particular way unless we had mass extinctions, which are probably what you get when you go ice ball, hot ball, ice ball, well, storm ball, over and over again. So let's look at this. This is a reconstruction of a snowball to greenhouse cycle. This is what we think happened 3 or 4 times during the Cryogenian. And so you would get the continents would break up. That's going to be associated with some volcanoes, perhaps. Eventually, those go down. We stop pumping CO2 in the atmosphere. CO2 is reduced. It keeps getting deposited on the seafloor and used up by plants and things. And so at this point, we're in a low CO2 time. And so too little CO2, and basically everything starts to freeze. The Earth does not retain enough of its heat. Space is very cold, and so the planet cools off. And if it cools off too much, if it only cools off a bit, you're just going to have some sort of freezing of the oceans. But if it cools off too much, you're going to have glaciers on the continents, ice in the oceans, and essentially you're going to be locked in this cycle. Now, underneath that ice, of course, there is always going to be geothermal activity. And so we're going to be having little mini volcanoes, black smokers, stuff like that. Those are going to pump out a lot of carbon dioxide, but it's going to be trapped under the ice. Eventually, the ice is going to crack somewhere. This is going to come out. It's going to fill the atmosphere. Now the world is going to start retaining heat, and it's going to take a while to thaw the Earth, for sure. But we're going to build up that CO2, first in the ocean and then in the atmosphere as it's released. And then we're going to eventually have so much CO2, because we trapped, thousands to millions of years worth of it, and then we released it all at once instead of having just a little bit that then gets converted by plants and into rocks. And so now we're going to have way too much CO2 in the environment, in the atmosphere, and that's going to lead to an extreme greenhouse where we're retaining way too much heat from the sun. Temperatures are going to skyrocket everywhere, and that's where you get the massive storms with this increased temperature. It stirs up the weather, as a dumb way to put it, but still fairly accurate. Anyway, that is going to be followed by eventually we're going to dump some of the CO2 into rocks. We're going to lay down really thick carbonate rocks because we're going to dissolve as much of that CO2 into the ocean as can be dissolved. That's just going to happen without anybody doing anything. And so eventually it is going to go back down. And so it's not a question of will the planet be okay? Because given 100 million years, the planet will self-regulate and it'll be cool. The question is, what happens to all the things riding on the planet during all of this fun stuff? Yeah, and the answer is bad things, real bad things. Yeah. So we have a hothouse cycle, an extreme greenhouse cycle, coming out of an extreme cold cycle. This is the end of the Pennsylvanian going through the Permian, and then at the end of the Permian, we got a real spike in temperature, if I remember right. And a ton of CO2 gets deposited right there at the end. And that is the marker for the greatest extinction that the planet has ever known. So, it's not good for the passengers when the car freezes over and then overheats. Yeah, or either of those things, really. All right, so what happened? When did it happen? Here's what we think. So we think we've got archaea coming from the Archean. Oh, neat, yeah. And also bacteria. Those start at the same time. Archaea start as a branch off of that. We start seeing some markers of like eukaryotic type sterols, cholesterols, in the way back here in the Archean and in the Proterozoic. Those are going to build up, and you also get the fungal type things like ergosterol, which is a modified version of cholesterol, or rather, I don't know, they don't start with cholesterol and change it. It's a different biosynthetic pathway, but very closely aligned. It has a lot of enzymes in common. And then true plants actually start going a little bit later, like land plants in particular, and proper modern-looking metazoan animals probably start at the base of the Cambrian or somewhere thereabouts. Yeah. The glaciations are happening here, here, and here. So those are the little arrows that are up there. How do you recognize a glacial sequence? Well, you get rocks like these. And we'll look, we have a nice sample of glacial till, which is fossilized in class. So down here we have our quartzite, and so that's great. And then on top of it, this is the glacial till. So this is like dirt and rocks, and look at all the different colors in here. You can tell these didn't form in place, because why would all the red minerals get together and then all the bluish ones get together and all the white ones get together and then all this sort of gray stuff stays apart from them? There's no reason. These are rocks that have been deposited in different places in different ways and have been scraped and rolled together. How can we tell it's scraping and rolling? Why, we can tell from the great big grooves that you get. And for example, on Mackinac Island, which is up in the Great Lakes, there are these great big glacial grooves that you can walk along. There are places you can slide down them. Yeah, they're a really interesting geological phenomenon. But glaciers are heavy. And underneath, at the bottom layer of a glacier, is this sort of sludge of rocks and mud. And that's what's actually being dragged across the rock. And it scours all the dirt off, all the plants off. It grinds down the rocks themselves. This is why some parts of the Midwest are as flat as they are. They got glaciered. Yeah, got glaciered pretty good. Okay, here's an example of a scratched pebble. So this is not the thing the glacier is going over. This is the thing that the glacier is carrying, but it's probably at the bottom of the glacier. And you can tell that this pebble is rotating around a little bit in there. It'll get dragged in this direction for a while, then it gets dragged in this direction, then it gets dragged maybe in this direction for a while. And so, it is scratching against a whole bunch of stuff. But that would be evidence that you have a glacier there. Here is this is what you get in the ocean when there's a glacier. You'll get sort of carbonates forming around this glacial till. But yeah, look at all the different colored rocks. That's going to tell you that this has been scraped together from somewhere. And yeah, this is like rock and soil that has been scratched off the surface of the land. There is bare rock where this used to be. Yeah, because this used to be covering it. Also, with glaciers, the glaciers are going to flow out over the ice or flow out, over the water. And then eventually the glacier is going to melt because water is warmer than ice. Yeah, you know that. Yeah. When the glacier melts, some of the rocks that are embedded in the glacier are going to fall out and they're going to drop down. And when they drop down, they're going to land in the mud and they're going to do this. They're going to make a little dent in all the layers of the mud so that you can tell this rock was dropped from above. Whereas these rocks, yeah, were also dropped from above. These are actually called drop stones. These are ice rafted debris. So the ice was out over the top and the ice melted and then the stones, boom, 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 boom. Yeah, drop and settle in the bottom and then eventually get covered over in nice smooth layers because the dirt is going to be deposited just gradually and the rock's going to build up in nice straight layers. And the reason why you would get discontinuities like that would be because something has happened. There's been a perturbation in the system, just like that. Here's an awesome drop stone. Look at this thing. Look at it bending, all those layers. Look at the new layers that are just piling up on top of it and eventually sort of flattening out as best they can. Yeah. There was nobody around at this time. This is from well over a billion. I think this is around 1 billion years old, actually. This part of Namibia. It captures the Ediacaran and some time before the Ediacaran. So there wasn't a person there to throw this rock into the ocean to have it land there, and there isn't any other really good explanation. This is too big to be carried along in a stream, really. And if it was carried in a stream, where are the other rocks of similar size? Why is this the only one that was carried? So no, this is probably from ice that has melted and then dropped a stone. An ice rafted drop stone. Yeah, that's the evidence. Here's another one. Look at that. Look at that. Look how nice that is in Namibia. Yeah. And then after the ice, when we get this thawing, then we think that there are, just like it says here, extreme winds and waves. And by the way, all the slides in this presentation come from this guy, Paul F. Hoffman, who has absolutely been an expert in this stuff. I don't know that he invented the Neoproterozoic glaciation, but he is certainly the one that has added the most evidence to this. And this is essentially the dude's life work. It's pretty awesome. Yeah. And so we think that, yeah, there would have been sustained wind velocities exceeding 20 meters per second. That is fast. The idea is that global temperatures are up around 40 degrees Celsius, which is way too hot, potentially during this time. And at this time, we see giant wave ripples. Giant wave ripples are going to be made underneath giant waves. And you can look under places that have giant waves now. After big waves come in, they make big ripples in the sand below them. And when you have little waves, you get little tiny ripples in the sand. And so from the ripple size, look at the size of those ripples on top of each other. These are the things that happen right on top of the glacial till, which I think is what we're looking at down here. And so these are the alternating, it's sort of carbonates, sand cemented together by calcium carbonate. And these are showing evidence of some pretty severe wave action. And if you can calibrate roughly what depth this is from some of the atomic waves that we talked about before, then you can say, yeah, this was, at a depth of about 10 meters, and yet still the waves are big enough that they're stirring up giant, sort of little, like little sand dunes, but underneath the ocean. And so that's a sign of extreme energy in the waves above. Because if you spend a lot of time looking around at the bottom of the ocean, it's mostly flat, except when you get near shore where the waves have action and will deform the sand. And yeah, deformations this big mean really big waves. So this is the succession that you find in different places all around the globe. Namibia, Svalbard, that's way up north, like past Norway, I think. Northern Canada, in Brazil, in Australia, in different parts of Namibia. So you will have these wave ripples. So this is the high energy thing. And then you'll have these aragonite cements. So this is when we're putting a lot of carbon away all at once. We're putting so much away that we're actually forming aragonite, which normally would not be stable because it's too soluble. The only way you actually make aragonite into rock is if there is so much CO2 dissolved and dissolving in that basically where everything is saturated. So that's what you see. And then, yeah, on the other side, you're going to get the actual sort of glacial till basically happening. And so here's another look at these sort of systems. So you're going to have big stromatolites, and so these are relatively near to the shore and near enough to catch some sun anyway. They're going to be covered over by gigantic wave ripples. So this is the extreme high energy as we're building up CO2. We're going to have a barite level, and I don't know what the geological significance of this is, but somebody does. And then you're going to have, the water's going to get a little bit deeper at this point. And so we're going to be depositing limestone. Yeah. Here is some of the barite. Here are a little aragonite coming off of it. This is the stuff that normally would not form in the ocean unless there are just extreme amounts of CO2 being deposited. And these are the successions that you see coming out of each of these glacial freezes. This may be a dropstone or a little chunk of carbonate, I am not sure, and it's got massive aragonite crystals that are growing off it, if I am understanding that correctly. Actually, no, those are barite crystals, pardon me, but the aragonite would come off of those. And so the idea is that at this time we are getting, basically, we have glaciers that are here that are covering everything, sea glaciers, land glaciers, and these are then melting, and so they're depositing a lot of rock, a lot of that glacial till, a lot of those drop stones into the ocean right here. And now the CO2 is really rising. So it heated up enough to melt these glaciers. And now that we're rising temperatures, we're getting a lot of weathering because there's no ice to hold things down. And so we will start to deposit some more carbonate on these little shelves. And then gradually we're going to have these sort of dry out a little bit. And so this shallow sea up here is going to dry out as we start to reform some of the polar ice caps, basically. And when that happens, the dried out material that the water was carrying is going to form these big, thick carbonate layers on these carbonate shelves, which were in just the shallow water areas. So that's what you get. That's our little cap carbonate cycle, our little greenhouse cycle. That's the thing that happened. What do the geochemists think about all this stuff? Well, they show us that there is a disturbance in the force, if you like. So watch the little line here, and this is excursions in carbon-13. So remember that plants are very good at capturing certain types of carbon and excluding other types. And so when you see big peaks up here, this means things are doing well, if I understand right. And when you see these troughs down here, this means that everything has died. Basically, like global plant life is in crisis. And I believe that is correct. And so at times when we get lots of animals basically developing and doing well up here, and so extinctions are going to be marked by negative delta 13C excursions. And then areas where there is glacial till, you're not going to be able to accurately measure This because you're going to get rocks that are coming in from different places, and so they're not reflecting what's happening here and now. They're reflecting what's been carried in and dropped on a spot. And so, yeah, these are the some of the different glaciation events that come within and just before the Ediacaran. This would be the Cryogenian just below this. So, yeah, this is the idea. We have in the Tonian, we have different steranes starting to develop, like some of the algae associated steranes. These are molecules similar to cholesterol. We get pretty much nothing deposited at this point. This is Snowball Earth. Almost everything is dead. Clearly not everything is dead because it comes out on the other side. And you start to get these animal type steranes really appearing, coming into the Ediacaran. It is plant type, and it is protosterols, which are like intermediate biosynthetic products, which were probably the terminal biosynthetic product at the time. So it's things learning how to make basically the types of cholesterol-like molecules that we see now. And so everything changed. We get a really different balance. We get far less of the plant type sterols, far more of the animal type sterols appear in the Ediacaran and then carry on into the Cambrian. So yeah, that's this is the story of how we got here. A really bad thing happened, and would these animal ancestors have come through if the Earth had not been essentially wiped free of life? I don't know. Would it have taken longer? Maybe. Would it have happened at all? Couldn't tell you. Couldn't tell you. But the shape of our evolution, the shape of the Ediacaran explosion, the shape of the Cambrian explosion that follows after is in, we think, direct response to these glaciation events in the Cryogenian. So there you go. That's the idea. That's the Snowball Earth hypothesis. There's the data for it. So thank you very much.